Hello, today we are going to use our talent informal specification to test if a number is prime or not. Okay, so let's proceed. As we can see from this picture, you have a lot of roads in front of you, and the formal specification just show you the way, show you the right road map that you can follow to reach your program correctly in a quick way. Good. So usually the roadmap start with informal requirement. All of us have informal requirements. Then you are going to translate it into logic, into mathematics, and do some checks there because the checks will be much easier than testing the informal requirement. And then if everything is going fine, I am going to translate it into code or generate test cases that I can use after I finish my coding, and finally I can reach the correct software. So this is like the steps you are going to follow today. Good. So let's see this problem. Uh, Testing some number is prime or not. What is a prime number? Prime number means it's a number that doesn't divide anything but just itself and one. So 2, 3 are primes, 5, 7 are prime. 9 is not prime because it divides 3. Okay, so we are going now to try to think about some way to come out a number is prime or not and see if this is correct or not. So what we call the first try, usually we can note that most of the numbers are odd. So if I can say that a prime number is odd, this statement is not completely correct and it cannot be used very well in computing for prime. Actually, it results in knowing a number is odd or not if it's prime. So usually I have to think of putting the prime number here in the conclusion part. Good. And also it contradicts with prime 2 because 2 is a prime number. Canonical form for this that can be used formally for proof. We just translate the implication into or and then negate the first part, the condition, so it will be not prime x or odd x. Okay, and then I can use it to make sure that I can check something. For example, odd 2. 2 is not odd. Okay, so not odd 2, it means that I can use resolution here and it will result in not prime 2. If I have not prime 2 but I know 2 is prime, so this is like contradiction because this rule is not completely correct. So this rule is contradicting with the 2. This is a very good example to know how to use resolution to make sure that I can check for the correctness of my program or my steps. So as we said that we have not, let's write in red, not odd 2, and with this canonical form I can just do the resolution because odd and odd, not, and there is no not here, x and 2. So x will be 2 and then I can just substitute for x equal to in here, so it will result in not prime 2, which is wrong because 2 is prime. Good. So let's try some good way to make sure that we can come out with the prime function. So let's give it a try. So what about this? This means for any number x, if it doesn't divide anything, it's prime. If it doesn't divide anything, it's prime. So let's see what is the problem with this. First of all, let's translate it into some canonical form that we can use in resolution. So I will just move this arrow implication to be or and then negate the first one. Here I just removed this So it means that either x divides y or x is a prime. This is just for one number, so this is like the trick or the bug. So let's see how to make sure we come out with something correct or not. Let's try to test something like here we have prime x, so we cannot say like prime 7, but I can say prime, not prime 8, and then I can use resolution now. So not prime 8 can match with this because I have x in here and I have 8 there, so x will be 8. So the remaining part will be this part, which and the x equal 8, so means 8 divides any number. So this is not correct, but we can just conclude 8 divides any number. Okay, good. 8 divide 4, 8 divide 2, but 8 doesn't divide 3, 8 doesn't divide 5. So this is like a slight bug or a small bug. What about resolution with something like here, this first part? So this means it divides. So what about it doesn't divide? X doesn't divide 3. So I can make some, 7 doesn't divide 3. So I can make some resolution with this. X equal 7 and Y equal 3. And the remaining part will be prime 7. So this is perfect. But what about something like this 9, which is not prime, doesn't divide 4? So again, I can just do resolution here, and it will result in prime 9, which is wrong. So usually you have to be careful because the condition you are saying could be wrong. It can have some negative errors or positive errors, so it can just have something which is not correct. So I have to make sure that I check my logic to make sure it's correct. Good. So let's do some second try. This is a second try. Here I tried to correct myself. I'd said that if any number x divides some specific at least one y, so it's not prime. So this is a bit part better than before, but here not prime. So this is like some evidence it's not prime. Okay, good. So the canonical form will be just the translate as we have done before. This will be or, and then I will have negation for this. And now I have to find substitution for y and x. X will remain a variable, but y, it's not a variable. It is some constant depending on x. So I would say here it's factors of x. So I'm replacing y by factors of x because it is just specific value or one value, two values, but not every value. So what does this say? Say if x divides some number, it means it's not prime. If x divides some specific number, it's not prime. For prime numbers, I would say uh, the first part will be true and the second part will be false. So let's proceed with some example. What about prime 7? Now prime 7 can do resolution with the second part, not, and there is no not here, prime and prime, x and 7. So x will be 7. I will substitute here. So I can end up with not 7 divides factors of 7, which means that there is no any number 7 can factorize. Okay, even it is like it's their factors or some specific numbers for it. So this is good. So everything is fine, but I just have to consider factors of 7 could be 1 or could be 7, the number itself, or 1. So I have just to make this restriction, which could be something in here. Before I do the implication, I can put here extra condition for y and x, which means simply that x should be have a specific range, or y should be between 2 and x minus 1. Good. So good. This is the third try. It should be the perfect try now. This is what we have done. It's the same like before, but I just added this part, which try to limit the choice of y to make sure that I have to choose something good. Actually, I have to consider here also maybe ascending or descending, because it can just shape the solution, as we are going to see soon. Good. So the canonical form will be here. Usually if I have A and B implies C, I would have not A or not B or C. This is the general form. So I have like three terms and or between them, and this is like what we call the canonical form. So it's ready. I don't have to divide it or split it into rows because it just contain or. Good. So what about something like prime 19? It can match with this x equal 19, and it will tell me something like this, which means that there is no number between 2 and 18, and 19 divides it. So this is like perfect. So I wanted to test something which is actually not prime, like some number divides some other number, like 8 divides 4. So 8 divides 4, it will match the first part. Good. X equal 8. Um, X equal 8, yes. And then I can say um, the remaining part will be this part. And if I know 4 is within the limit between 2 and 8, I can also say not prime 8, and this will be correct. So I can just have some conclusion to say the number is prime or not prime, and this will be very good for me to solve my problem very well or very correctly. Good. So now let's use this information to translate it into a program. So from the logic, which I translate the informal requirement, and then I did check the formal form, and finally I can just proceed with the programming or the test cases, as we are going to see now. Here I have the formula for logic, first order logic. Now I'm going to build the function. The function starts with some Boolean function called isPrime to test if x is prime or not. This is similar to this predicate, so the predicate will be the head of the function, or the first line, the prototype of the function, and then I go inside the body of the function. So the function say I'm going to test numbers from 2 to x minus 1, which is this part, y. I'm looking for y, and then if a number x divides this y, I can just return 0, which means this is not a prime. If everything goes fine and the loop finish correctly without return, I would say return 1, which means the number is now 1. The number is now prime. Good. This is like the mapping part, or the analogy between the logic and the code. And finally, the for loop are shaped by these limits I put on the y. I could also do something else, which preparing some test cases. Test cases, because maybe someone can develop the program in a different way, and I just want to make sure I test it correctly. So here I have this formula, and I just wanted to have some test cases ready. So if someone finishes the coding, I can just tell him this is my code. So the test is based on condition. I have here some condition. Y is between these values. x divides y and not prime x. So maybe I can just have some combination true or false for each one of them. This one usually I will leave it as it is because usually I have a for loop inside my code and y is limited to be between 1 and x. You will not be able to do y outside this range, so it will be, I can just forget this. Okay, so I have like 1 and 2, so maybe I can just produce some number that can divide some other number, and then I can say this is prime or not, and also I can test it with prime or not prime number. So let's see. Good. So maybe I can just start with prime 17. So x equal, this is like the two test cases, one of them prime 17, which using resolution can tell me that 17 doesn't test anything, so it should return 1 because inside the loop it will not be true for any value of y. The second test case is x equal 8. X equal 8 here, and I will try to have some number that 8 divides like 4, and then I would have something in here like false, and this could be true. 8 divides 4 equal true, and this will produce prime 8 to be false. Good.